The Work Package 4 of the FutureCom project regards the measurement methods for passive intermodulation in communication systems. The partners involved in this work package are 3 national metrology institutes, PTB, CMI, and LNE, 1 designated institute, ENTA, 1 academic institute, the University of Applied Sciences of Aachen, and 3 industrial partners, Rosenberger, Anritsu, and Nokia. The work package is focused on continuous wave signals in mobile communication systems, and its goal is to develop and validate novel measurement methods to evaluate the passive intermodulation of radio frequency electrical signals used in communication systems. From a top-level view, the work package was divided into 3 main tasks. The goal of the first task is to establish precise and traceable radio frequency power and S-parameter measurement capabilities in industrial RF connector systems. This work was carried out on 4.3, 10, and 7/16 connector types. The second task focuses on the measurement of PIM signals using the traceable RF power and S-parameter measurement capabilities developed in the previous task. Within this project, several PIM measurement capabilities are established at the partners' laboratories. The purpose of the third task is to test PIM testing under different measurement conditions such as different power levels, different ambient temperatures, and different relative humidity, etc. As the most important results of the first task regard, S-parameter measurement capabilities for 4.3, 10 and 7/16 connector types were established at PTB and LNE laboratories. For a bilateral comparison between PTB and LNE, a matched load was used as a traveling standard by PTB and LNE. The measured quantity was the reflection coefficient S11 of the 4.3, 10 matched load. Good agreements are obtained between PTB and LNE results, as shown in the figure, which shows both PTB and LNE results. The second significant result of this task is the establishment of RF power measurement capability. An RF power source with 2 RF transmitters was used as a traveling standard. The RF power of each transmitter was set to be 36 dBm, 40 dBm, 43 dBm, and 46 dBm. PTB, CMI, and INTA measured the RF power of each transmitter at the different specified RF power levels. The RF power source was connected in series with an RF attenuator and a power sensor using some suitable adapters previously characterized. The measured RF power obtained by PTB, CMI, and INTA were compared against the reference RF power. Good agreements are observed between the RF measurement results and the reference RF power. For PIM measurement comparison, 8 traveling PIM standards were used for the measurement of PIM signals. 3 tunable PIM standards have a PIM level range from -80 dBm to -110 dBm, and 5 PIM standards have a PIM level range from -70 dBm to -125 dBm. The yielded PIM results by the partners who were involved in the measurement are plotted against the PIM reference as shown in the example above. It is observed that the PIM uncertainty at low PIM levels is larger than at strong PIM levels. The increase of PIM uncertainty at the low PIM levels is mainly associated with the errors introduced due to the self-intermodulation, since the distance between the self-intermodulation of the measurement system and the measured PIM level becomes smaller. The main uncertainty contributors of scalar PIM systems are the RF power of the two-tone signals, the RF receiver, adapters, and the uncertainty associated with the residual PIM noise. For strong PIM signals, the RF power, receiver, and adapter uncertainties are the major contributors to the PIM uncertainty. Instead, the residual intermodulation is the major contributor to the uncertainty budget at the low PIM levels. The main uncertainty contributors of vectorial PIM systems are the SO calibration standards with adapters, the power sensor, the phase reference, the VNA drift, the VNA linearity, and the VNA noise. The power sensor and the linearity of the VNA system are the main contributors to the PIM uncertainty of the strong PIM signals. Instead, for low PIM signals, the noise is the main contributor to the PIM uncertainty. It is very important to investigate the impact of the measurement conditions on the PIM measurement. This was the goal of the third task. In particular, the impact of DUT temperature on the PIM measurement, the impact of RF power on the PIM measurement, and the impact of relative humidity on the PIM measurement were analyzed. The analysis was carried out by changing only one quantity at a time, while the other quantities were set to their default values. As regards the impact of DUT temperature on the PIM measurement, a remarkable excursion over 12 dB of PIM level is noticed in the cold part of the cycle, within the range of temperatures where condensation and freezing may take place inside DUT. Furthermore, a smaller variation is noticed over 50 degrees Celsius. Generally, PIM is strongly dependent on the DUT temperature. As the impact of the relative humidity concerns, the PIM performance was almost independent from the environmental humidity. Only a little variation is noticed from a relative humidity equal to 70% upwards. As the impact of the RF power on the PIM measurement, the PIM level increases as the RF power increases, and the rate of increase depends on the DUT nonlinearity characteristics. This project has received funding from the MPEER program co-financed by the participating states and from the European Union's Horizon 2020 Research and Innovation Program. For more information regarding the project, you can visit our website, follow us on X, or join our LinkedIn discussion group.